height h, that is at this height, your potential energy is said to be mgh, which is the formula for potential energy. When you remove this proportionality constant, we get equal to and proportionality constant with the x, that is the displacement you get. Since a is nothing but acceleration due to gravity, it becomes mgh and minus mg small letter h. So this is your kinetic energy. Hello everyone, I'm Brinda from Department of Physics. So let us all deal with the chapter Work, Power and Energy, that is our chapter 6. So now let us see what exactly we study in this case of work, power and energy. So first of all, what is meant by a work? So work is nothing but the forces exerted to an object and the object is displaced. So there is a displacement of an object. So by looking at the displacement of an object, there should be an external force which is exerted on an object. So we can say that the force along with the displacement altogether gets you the work done. So here we have two concepts for the work to be done. One is your potential energy and one is your kinetic energy. So kinetic energy means the work is being done and the potential energy means the work is about to start. Okay, that means to say potential energy. So here we can derive one of the important concept over here, that is conservation of mechanical energy. How do you say the mechanical energy is said to be conserved? Before that, what is a mechanical energy? As I told you, if a work has to be done, there should be an existence of two types of energies. That is, one is kinetic energy, another one is potential energy. So the energy, mechanical energy can be of two types. One is potential energy and another one is kinetic energy. Here we are checking the mechanical energy means two sets of energy, how exactly it works. And we will have to check on the conservation. That means initial whatever value we have got, final also the same action has to be got. So that kind of a concept is called as your conservation. The energy is said to be conserved. One complete kinetic energy is completely converted to potential energy. So energy cannot be created or it can't be destroyed. It can be transformed from one form to the other form. It just takes the transformation from different forms to forms. Okay, but it will never be created or it will never be destroyed or cancelled. Is it clear? So now consider a ball of a mass m. So suppose if this pink ball is of the mass m, it is said to be dropped from a cliff and the cliff height is given here, that is h, capital letter H, as shown in the figure. So we have V0. V0 is nothing but equal to u, which means to say it is initial velocity. So initial velocity of a ball is said to be 0. So now when it drops, this is during each stages, what happens? We'll have to calculate one value at this stage. So initially it comes and falls down here. So from the center to the base, what is the height? It is the small letter h. So we have to differ from this h to that h. So now a ball is made to fall from the top. So we know what is V0 or initial velocity, that is said to be 0. So now at height h, that is at this height, your potential energy is said to be mgh, which is the formula for potential energy. Okay, so this h turns out to be mg and capital letter H because we are calculating at this height. At this height we have this h, capital letter H. Okay, and your kinetic energy at the cliff, that is at the top, is said to be half mv square. Your v square is nothing but your initial velocity you're calculating, and there is no movement or of an object at the top, that is at the start. At the start, the potential energy is very high, wherein kinetic energy is 0. So this comes out to be 0. So what is total mechanical energy? As you know, total mechanical energy is nothing but sum of potential energy and kinetic energy as given here. So your potential energy is mgh, your kinetic energy is said to be 0. So the final value you have is mgh. So total mechanical energy, in short I can write TME, total mechanical energy is mgh. This is said to be equation 1. So what is the total mechanical energy at this point? We got it. So it is mgh. Now let us check what is the mechanical energy at this point, wherein here we have potential energy but zero kinetic energy. Here both are also equal, but here zero potential energy and maximum kinetic energy. So for that case, let us see the another total mechanical energy at this point now. So we have potential energy at that point, that is at height small letter h. So it is mgh. And kinetic energy we have half mv square. So half is okay. M is the mass of an object which will never change. But what is V here? How can I give the V? So we have V square minus U square is equal to 2as, out of which your U square is said to be 0. So I can consider V square is equal to 2 into A into S is nothing but the height. So how can we consider this? We are calculating the height of this. What is it? So out of the total, we take up the so much height which is actually mentioned. So it is out of total. I'm just subtracting this height which is already given, that is small letter h. We don't have any value. We are just playing with the alphabet. So we'll have to take up the alphabets itself. So it is h minus h. So your s turns out to be capital letter H minus small letter h. So V is equal to root of 2 times A of h minus h. We have h minus h. Now apply this V on this equation. So we have half m. What is V square? It is root of 2 into A into h minus h the whole square. So here we can cancel square with square root. So we have 2 and 2 gets cancelled. M into A. A is nothing but your acceleration. Since A is nothing but acceleration due to gravity, it becomes mgh and minus mg small letter h. So this is your kinetic energy. So what happens to total mechanical energy now? Therefore, total mechanical energy turns out to be sum of potential energy and kinetic energy. So your potential energy here, it is plus mgh, and kinetic energy is plus mg capital letter H minus mg small letter h. Both are same with opposite signs, so cancel 2. So we have total mechanical energy is equal to mgh. So this equation is said to be equation 2. So we got to know what is the total mechanical energy at this point. So the third, that is first is over, first point over, second point over. Now third point, what is the total mechanical energy at this point is what we will have to calculate. For that also we have the same components. That is again, we have potential energy at the bottom, that is the ground level, it is 0. That is, suppose this is a ground level. Here potential energy is high, kinetic energy is said to be 0. Here both are equal. And here it is potential energy is low and your kinetic energy is high. Completely it is converted. So potential energy is 0. And what is your kinetic energy? It is half mv square. Out of this, which if you just calculate, your v square is equal to u square plus 2as. U square is said to be 0. So v turns out to be v is equal to 2 and acceleration due to gravity is g. The complete height from the top to bottom, it is said to be h. So it turns out to be h. So root of. So apply the same equation in kinetic energy. So we have half m of root of 2gh the whole square. Square square cancels, 2 and 2 goes. So you have mgh, that is your kinetic energy. So total mechanical energy is equal to put sum of potential energy and kinetic energy to give you 0 plus mgh will give you the total mechanical energy as mgh. So this equation is said to be equation 3. So here we can see that equation 1, equation 2, equation 3, both are also having the same component with respect to mass, acceleration due to gravity as well as height. That means to say the energy is said to be conserved. Initial energy, total mechanical energy is equal to the final one, whatever we have got. So it is said to be conserved. That holds good for this conservation of mechanical energy. So now let us just skip on to the potential energy of the spring. I hope you know what is meant by a potential energy. It's the stored energy which will later transform into work done. So stored energy is getting converted for the work to be done. That means to say stored energy is potential energy, and the energy which is actually executed when the work is done is said to be kinetic energy. So now we are dealing with potential energy of what? It is a spring. So I hope you have seen a spring. Okay, spring which in case when you pull it, it extends, and when you leave back, it goes back to its original position. It will just have an oscillations for certain interval of time, and then it comes to its rest, that is equilibrium position. The same concepts we are actually checking out here. A spring when stretched from its mean position means it is its rest position. Okay, it tends to restore its equilibrium position by exerting a force which is equal and opposite, which means to say there is a force which is exerted directly proportional to the displacement. Correct? When you apply certain force, when you just pull it, it is directly how much ever force you apply, so much displacement has been taken place there. So when you remove this proportionality constant, we get equal to and proportionality constant with the x, that is the displacement you get. Correct? So as you remove this proportionality, we have got a constant, and here the constant is said to be in a negative form. Why this negative form? It is getting restored back to its original position. Restoring back in the case of plus and minus component. Towards this axis is plus component, coming back is minus component. So restoring effect is with respect to your minus symbol, sign. Okay. So with respect to this, we have A, B, C images wherein a spring is connected to a block and the block is pulled forward. So it is a positive concept, whatever is shown with certain amount of force what is applied. And as you leave the block, what happens? It bounces back in a negative axis. Okay. So in order to have a equilibrium position or the position which is at rest or a mean position. So what do we do with this? We just check on to the how exactly it works. We have to know the conditions of the potential energy, conditions of the spring at this case. So how exactly it works? And we have the work done is equal to force into the displacement which is given. So this holds good for the change in work done. So change in work done is equal to force which is applied to the changes which observed in displacement. Now it is clear with respect to the equation. So now we'll have to check what is this force. Force is nothing but whatever we had got in a previous condition, that is dW is equal to force is minus k into x into dx. So this is just a component of one single action. Suppose if there are n number of actions like this, we'll have to have a net work done by that spring, total work done or a net work done. How do you actually calculate it? Because for this calculation, we just use our integration part. So how do you use it? Integration of dW is equal to integration of minus k into x into dx. So you have W is equal to integration from where to where? From initial condition, that is, if suppose this is the initial term, you have xi is the initial condition and this condition, this term is called as xf, initial to final. So the distance it makes as x. So here we have initial xi to xf, initial displacement to final displacement. Since minus k, that is a constant term, we take it outside. So we have integration of xi, xf into x into dx. So on integrating this, we have minus k x square divided by 2 into xi, xf. This is with respect to a formula. We just apply a formula to this. And then we have this equation, and dx, it becomes a proportionality, that is integration constant arises there. So now Substituting these forms, we have W is equal to minus K xf square divided by 2, and we have minus of minus, that means to say plus k xi square divided by 2. So W is equal to, we can interchange it and write it as k is a common out, k xi square by 2, and we have minus k xf square divided by 2. Either we can take it common out or else we can retain in the same way. This is one of the condition when object is said to move from initial to final conditions. The work done is said to be in this form. So next, this is the first concept. And what is the next concept? As you all know, from initial condition, it is brought to the final condition. Again, as we leave the block, from final, it runs back to initial condition and it tries to be at rest. That means initial condition itself. So it is kind of a cyclic process. So this process is called as a cyclic process. So here, it's the same process what we take, but the conditions what we take will be initial to initial. So again, apply the same concept. Integration of xi and xi dw is equal to integration from initial to back to initial minus kx into dx. So when we just apply this, we have w is equal to minus k is taken outside. So apply the integral condition. So we have a, due to the formula, we get this equation, and xi we have. So w is equal to minus k xi square divided by 2, and minus it becomes plus k xi divided by 2. This is nothing but half mv square concept. Okay. So here what happens? Minus and plus cancel. So what do we have? The work done is said to be 0 at this condition. From initial to initial, when a block moves, the work done is said to be 0 itself. So that is your second set of concept. So because of these two set of derivations, we get to know that the force of a spring is said to be position dependent. The force depends upon the position, and work done here depends upon the initial and final condition. There, the work done from initial to initial condition is said to be 0. That means from initials, in a cyclical process, the work done by a spring is said to be 0. These are the conditions for you to actually give it is a conservative force. The spring is a conservative force in nature. Next, we have our potential energy. So with respect to potential energy, if you go, potential energy in case of your initial condition is said to be 0, but potential energy in case of your final condition is said to be maximum. So we call it as x due to this condition, that is maximum, it is x over here. Okay. So we have uxi is equal to 0 and uxf, that means to say it is a potential energy. So now we already know that the work done is equal to, you can actually convert this work done. Work done means there is an energy which has been there. Yes. So before the work is done, there is a potential energy. That is also right. So here we can give, it is a difference between final potential energy to the initial potential energy. That means the potential energy is converted completely into the work done. So what is the work done? We have this equation. This equation we can't substitute because it is said to be 0. Here there is a condition from final to initial. So potential energy is completely converted to the work done. So work done, it turns out to be half of k xf square minus half k xi square is equal to u of xf is, it is x and minus, and this is nothing but 0. So this xi, since it is initial condition, it turns out to be 0. So this goes with this itself. So we have half kx is equal to x itself. So this is actually the value. So this x can turn out to be u as well, because this turns out to be a potential energy. So half kx is equal to, instead of u of x, you can just take it as u itself. So this is the potential energy of the spring, is what we know from this derivation. So next we are coming up. So next let us check on various forms of energy and the laws of conservation of energy. So here under this we study only this concept, that is conservation of energy. What is exactly the conservation of energy tells? That is, energy can neither be created nor destroyed, but it can be transferred from one form to the another, like kinetic energy is transformed to potential energy and potential energy is transformed vice versa, and chemical energy getting transferred to electrical energy in case of your battery, or else potential energy is getting transformed as your electrical energy. All these things also, this goes with respect to your water turbines rotating due to the force of your waterfalls, and finally it is getting converted into electrical energy. All these concepts comes under an example for this law of conservation of energy of this law, that is, energy can neither be created nor destroyed, but it can be transformed from one form to the other form. Next we are going on to power. So what is meant by a power? Power means it's the rate at which the work is done or energy is transferred. So power is equal to work done in certain interval of time. So what is work? It is force into displacement, correct? So displacement with respect to change in time, if we give, power becomes equal to F into change in displacement with respect to time. It comes out to be velocity. Either we can go with this equation or with this equation. What is the SI unit of a power? SI unit of a power is said to be watt. Even the other way, 1 horsepower is equal to some watt it has got, that is 746 watt. This one you will have to remember for your exam, in the exam point of view. That's all about your power concept. And next we have collisions. This is what we study in work, power and energy chapter. Collision means what? Colliding. One object colliding with the other object, as you can see here. It is interaction between two or more particles when a force is exerted. Okay. So there are two types. One is elastic collision, other one is inelastic collision. So as you all can see, one is elastic here, one is inelastic here. It's very simple to understand. Elastic collision means as you just throw a ball bounces back. That means there is a kinetic energy, there is momentum. But it is said to be conserved in nature. Okay. But in case of inelastic collision, the object is going and hitting another object, that is a car probably. So if that's the case, if this is a condition, the kinetic energy is getting transformed to some other form of an energy and the momentum remains the same. So that is actually the difference between your elastic collision and inelastic collision. We at least regain its shape or regain its position back towards a normal point in case of elastic. But in case of inelastic, once the position or once the rigidity is destroyed, it is completely destroyed. We can't regain it back because it's converted to some other form of energy. So here, collision, differences between these are important, students. You will have to know elastic collisions and inelastic collisions. In the case of elastic collision, no loss in kinetic energy in the system, but there is kinetic energy is lost into different other form of energy. Okay. Here in this case, kinetic energy and linear momentum both are said to be conserved there. The total linear momentum is said to be conserved. Here in this case, the impulse on the first object is equal and opposite to the second. But there, impact and deformation, whatever is there during collision, leads to generation of heat or sound energy, any sort of energy that is transforming from one form of energy to the other form of energy. That's all. So in today's class, we have studied about work, that is what is work done means, what is the total mechanical energy in case when the work is done, that is with respect to kinetic energy and potential energy we have studied. What is meant by a power, that is a small bit concept of this chapter, and what is meant by collisions, types of collisions, elastic and inelastic. That's all for today. Let us all meet in the next session with the next upcoming chapter. Until then, have a good day. Thank you.